Hello students, and welcome to section 10-1 continued, the square root function. So thus far, if you recall, we have already talked about in example 1 key features of the square root function. As we kind of revisit this a bit here, and of course taking a look at the graphs again, f of x equals the square root of x, using minimally 3 points, and if you remember, they used 5 points in their analysis. 0, 0 must be used to start with as the minimum point. 1, 1 is certainly nice to use because the square root of 1 is nicely 1. And then I would argue 4 is also nice, the square root of 4 of course being 2. If you pick numbers beyond 4, 9, and 16 are great because they are also perfect squares. Now, as you could see, and hopefully you recall, you don't have to pick perfect squares, but you might not want to venture down that path knowing that the square root of 2 and the square root of 3 are not nice rational values. Your graph will take shape accordingly, if you recall, via Desmos. And yes, you could also use your graphing calculator if you have one. I do urge, though, that you try these problems first without a calculator, as we discussed. The square root function, as we also discussed, must also, or always, start by denoting that the radicand must be set greater than or equal to 0. That sets the stage for doing all of your work and making sure that you start appropriately at the minimum point provided. A couple of revisions that I did actually make after the notes were presented. Yes, we did use Desmos to come up with this graph, and yes, we did use Desmos as well to come up with this inverse graph. The inverse of a quadratic is a square root and vice versa. These are inverses of each other. So what I had actually taken the extra step here after the fact for you is take the function and flip it such that this is the inverse. And yes, if you were to graph the other half, you'd have a full quadratic. So this, again, this is a representation of if the function happened to be just y equals x squared. So my revision here, not only have I flipped it for you, but I'm also going to exclude that technically, because as it turns out, the inverse of the square root is just half of the parabola. And I've also denoted, as you can see, again, x is greater than or equal to 0, because we're only technically wanting to see those x values as such. Here, again, the x values are greater than or equal to 0, but so are the y values. And similarly, so are the y values here. So this is just a nice connection to be made with regards to graphing square root functions. Okay, example 2, translations of the square root function. Again, I do urge that you take a look, possibly using Desmos as you're doing these things. How does the graph of g of x equal the square root of x plus 3 compare to the graph of f of x equals the square root of x? Again, recall that f of x equals the square root of x is our parent function. Graph each function. Okay, so I'm going to uncover this, and yes, again, you're going to see some very similar things take shape. Now, if you did not use a calculator here, the first graph, of course, we already deciphered on the prior example, noting that 0, 0 is a good point, as is 1, 1, as is, let's say, 4, 2. You can plot those three, and there's your square root function. As it turns out, the difference between the red and the blue function graphs, as you can see, is simply a shift of 3 units up from blue to then red. So instead of 0, 0, you're up at 0, 3, and so on and so forth. For each value of x, the corresponding y value is 3 units greater for g than it is for f. So as we can see, the graph, as I denoted, already has a vertical translation, again, up 3 compared to the blue. And the translation is a result, again, of adding a constant to the output of a function. The domain for both functions is x greater than or equal to 0, while the range for the function is y greater than or equal to 0. So the range of the g function, and again, that was the f function we were referring to, the blue. The red function actually has a range of y greater than or equal to 3. So again, because our first point is 0, 3, it is again true that x still needs to be greater than or equal to 0, denoting that x in the root there, it's the radicand technically that we're setting greater than or equal to 0. However, even though the domain is the same, comparing blue to red, the range is not. The range of the red again is y greater than or equal to 3. So now let's take a look at another example here, part B. How does the graph of this, g of x equals the square root of x plus 3, compare to the graph again of the parent, y or f of x equals square root of x? So again, graph each function, and as you can see, I'll uncover that, and not surprisingly, again, we see that the blue function, again the parent function, is denoted where you have 0, 0, 1, 1, and 4, 2. Those three would be good as usual to start with and minimally use. The red function, on the other hand, if you can see here when you compare the two, appears to be a shift of 3 units to the left. So if I were to just look at 0, 0 as the initial point there, shifting at left 3, not surprisingly it looks to be at negative 3, 0. And I say not surprisingly, if you consider the radicand of x plus 3, think of setting that greater than or equal to 0. And I'll explain more in a moment. For each y value, the corresponding x value is 3 units less for g than it is for f. The graph of the function, as I denoted again, is a horizontal translation comparing to the blue parent function, or 3 left. The translation is the result of adding a constant to the input of a function. Well, the domain is x greater than or equal to 0, and the range is, well, it's going to be y is greater than or equal to 0. Okay. Let me speak about, the domain a little bit more in depth. If I need to correct myself, I'll excuse myself in a moment if need be, but the domain of f, the blue function, is technically x greater than or equal to 0, while the domain of the red is x greater than or equal to negative 3. It's the range that is the same for both. They're both technically above the x-axis. So y is greater than or equal to 0 for both. But again, because we note the first point at negative 3, 0 for the red function is what we're observing, x must be then greater than or equal to 3, while the blue function is the same as before, where x was greater than or equal to 0. I did denote again earlier that if you set x plus 3 greater than or equal to 0, you do then in fact get this. Subtract 3, and x in fact is x, as you can see, greater than or equal to negative 3. So that x value, from there, making an xy table, start at negative 3 and work your way up from there if you wanted to plot, obviously, 2 more points or more if you'd like. If we continue, we'll see here in example 3, a rate of change problem, rate of change of the square root function. For the function f of x equals the square root of x, how does the average rate of change from x equals 0 to x equals 0.3 compare to the average rate of change from 0.3 to 0.6? So as you can see, here's our square root function. Not surprisingly, it should look very much like what we saw earlier at 0, 0, for example, as an ordered pair. There's another ordered pair at 1, 1. But because this is a zoomed in version of the parent function from earlier, those are really the only 2 points again to relate back to. If you continued off to the right, of course, another point like 4, 2 would be noteworthy. We're not seeing those, but that's fine because technically we only want to make a connection with 2 points, 0.3, f of 0.3 and 0.6, f of 0.6. So quite literally you'll plug in 0.3 and 0.6 to see what those particular y's are. And then you'll find, using some additional math, the average rate of change. Additionally, denoting again things we've done in the past in similar functions. Evaluate the function for the x values that correspond to the endpoints of each interval. So f of 0, Square root of 0, in other words, that's easy. That's 0. Continue, plugging in 0.3, the square root of which is 0.548 roughly. And then 0.6, the square root of which, 0.775 roughly again. And then step 2, that demands you to actually do the average rate of change analysis, where if you recall, like we've done in the past, we'll be using a very similar model to where you'll be doing y2 minus y1 divided by x2 minus x1. So if you recall, it's the slope formula. So f of 0.3, which is the y, technically again 0.548 as you see back here and again here, minus f of 0, which again we said was 0. Okay, and then divide that by the difference in the x's, which again we said was what? 0.3 and 0. Okay, so if we divide the difference of those and the difference of those, you should end up with 0.548 over 0.3, or approximately 1.83. So from the 2 points, 0.3 to 0.6, we can do the same math. We're not quite done, of course. So we're basically going through and doing y2 minus y1 over x2 minus x1 again, but we're using these 2 points as opposed to those 2 points. Okay, so we do the math. I'll let the actual subtraction speak for itself, and division, of course, then in the next step. So 0.227 over 0.3, which ends up being approximately 0.757. So when it's all said and done, now we have, of course, those two slopes, or average rates of change, same thing. So between 0 and 0.3, again, we got 1.83 versus 0.757, which of course is a smaller number. So the average rate of change over the interval between 0 and 0.3, and that compared, of course, to 0.3 to 0.6, this is bigger than that. If you look at the graph as well, if I go back here for a moment, you could pretty obviously see, I would argue, that this slope, this blue line connecting these 2 points, this blue slope, let's just say, is steeper than this green slope. Okay, so the average rate of change between those two versus those two is clearly a larger slope. I say steeper because it looks to be. All right, example 4. 2 plans are being considered to determine the speed of a theme park ride with a circular wall that spins. Plan A is represented by the function with the graph shown. The ride shown in the photo is an example of Plan B. If the ride has a radius of 3 meters, which plan would result in a greater speed for the ride? Okay, so as we take a look, we can see there Plan A. And yes, we have points of which you can see what, 0, 0, and what appears to be about 6, given an x value which appears to be 3. Okay, and they tell you that, of course, to get that that approximation more honed in on. So those particular points speak to then 2 of which are on that function that you see. It is a square root function, as they describe. And if we scroll down, Plan B is represented as such. You've got f of r equals 5 times the square root of r, where r is the radius of the ride and f of r is the speed. Compare the plans. Plan A versus Plan B. The graph of Plan A shows that the corresponding speed at a radius of 3 meters is about 6. And if you plug in 3 into the function, again, 5 times root r, r being 3, so 5 times the square root of 3 being 8.7. The ride using Plan B has a speed of about 8.7 when the radius is 3. So with that radius, the speed of the ride using Plan A is 6 versus 8.7. So the ride using Plan B has a greater speed for that particular radius. I do urge that you try some of those try-it problems that follow the examples, and we will certainly touch base while we're together in looking at some of these problems, but also doing some of the graphs to verify what we've done.